In recent years, Greater Manchester has seen more frequent and more severe sinkholes. In 2015, a 12-meter deep sinkhole opened up on Mancunian Way, which disrupted traffic for 10 months and took £6 million to repair. Sinkholes typically develop slowly underground over time. Current methods of geophysical survey are expensive, require manual labor by experts, and are limited in both area and time covered. Therefore, this project presents a proof-of-concept towable measurement system to detect early sinkholes on primary transit routes. The solution is envisioned to be towed by existing council vehicles to provide cost-effective, regular survey which cover a wide city area. Measurements from the chosen sensors are interfaced to GPS to profile subsurface conditions and generate a survey map. Additionally, the system is augmented to also detect potholes, which cause over 10,000 vehicle breakdowns in the UK annually. This pothole detection is achieved using a 2D LiDAR. The GPR transmits EMF wave, which reflects off materials at permittivity boundaries to provide rich subsurface analysis. This data is collected in the form of a radargram, which shows the reflection signatures of detected objects. Real-time processing was implemented to detect scanned object on the radargram. This includes low-pass filtering to remove noise and background removal to segment the signatures. Testing in a controlled sandpit environment demonstrated the GPR's ability to detect a subsurface void represented by an empty plastic container as small as 170 mm in diameter and as deep as 200 mm. These tests were extended to an outdoor dirt pit environment, which showed similar penetration depth and detectable void sizes. The properties of the mineralized soil in Manchester allow a metal detector to detect the pockets of air that exist in the soil. A bespoke metal detector was designed and constructed which featured a PCB, microcontroller, a transmitter coil, and 2 receiver coils. The microcontroller connects to the PCB and implements software adapted in C to control its operating frequency and perform FFT. Software was developed in Python for serial communication with the microcontroller, data extraction, and real-time data visualization of frequency domain magnitudes. Real-time processing was implemented to detect voids, which includes low-pass filtering to remove noise, and gradient analysis to detect the drop in magnitude. The final product is a metal detector with a detection range of approximately 500 mm that can detect magnetism from the soil, and hence can pick up on subsurface voids. For pothole detection, a 2D LiDAR is used, with a field of view of 86 degrees, covering 0.9 meters of lane. After the development of a specific data acquisition software in Python, the sensor provides a 2D point cloud of the surface under the sensor. The 2D point cloud then goes through the team-developed processing algorithm that uses a combination of filters and slope gradients to identify potholes in the sample cloud. The data from each sensor is then fused and integrated with GPS, and plotted to generate the survey map. The sensors were securely enclosed in a constructed towable chassis to avoid vibrations and enhance noise from wire crosstalk. The metal detector coils are positioned far from the electronics to minimize background interference and improve sensitivity. The assembled system was tested outdoors, over a hole 700 mm wide and 350 mm deep. Results showed that the GPR and the metal detector function correctly together, providing promising results for this proof-of-concept project. The final prototype can simultaneously combine data from the GPR and metal detector to find subsurface cavities suggestive of early sinkholes, and additionally use the data from the LiDAR to detect potholes. The data can be collected at 5 miles per hour, and the GPS is accurate within 3 meters, as specified in the norms of the project. The system is able to detect subsurface voids in dirt as small as 170 mm wide and 200 mm deep. It can also detect potholes as small as 40 mm wide and 40 mm deep. As a proof-of-concept project, future works may focus on improving the specification of the system for practical operation. Sensors should be upgraded to allow greater penetration depth and resolution, as sinkholes can develop tens of meters beneath the surface. For the metal detector, penetration depth can be scaled up linearly by increasing the coil diameter. Higher sensor sampling rates as well as a dedicated FPGA for faster processing would allow for faster vehicle speeds. This would be necessary before operations on real roads. Furthermore, the chassis should be enhanced to provide protection against operational hazards such as traffic and weather.